So, welcome everyone to session one or part one of robotics mechanics. In this part, I will talk about some terminologies and histories about robotics mechanics and also about one important topic, which is the mobility. Now, machines have been evolving for several decades now, and traditionally, or basically historically, machines started as pure mechanical systems. For example, pure mechanical cars, and have been evolving over time. And recent machines basically they start to contain other part like mechanical, electrical, and recently they're more focused on also on smart uh, uh, or intelligent part, which is the artificial intelligence. Now, regarding terminologies, the mechanical, electrical, and electronics or software part, they form what is called mechatronics, which is a field of engineering that basically uh, targets building or learning how to build complete machines and mainly smart machines like robots, for example. Yes, robotics was basically it's an application of mechatronics, and of course, the mechanical part is very crucial part in any machine and mainly in robotics. Uh, and also, the safety of robots actually comes first from the well design also and analysis of the mechanical part of it. So just basically materials that I've used for this course. There's mechanics and mechanisms, which basically talks about position, velocity, acceleration analysis, and kinematics, and so on. Same as mechanics or machines and mechanics. So there are somehow similar books, and we have basically the fundamental of machines component, which is this cares more about machines design or machines components design, which is basically I'll talk about later. But for example, if I have a mechanical or a physical objects in my car or in my machine, uh, and or basically this object is subjected to some kind of load, let's say, and temperature. The question would be, let's say, what is the dimension of this part that is able, or basically with this dimension, this part is able to resist, let's say, this load and avoid fatigue, and also, of course, avoid um, breaking down. So this is basically what is mechanical just briefly, of course, what is mechanical component design about. The last book is about fundamental of robotics mechanical systems, which is here more about robots mainly, because the other three books are about machines in general, and this one is about robots specifically. Now, mechanical design in general has three processes or components. So there is the mechanics, there's industrial design, and there's a component design. As you see in the figure, basically it's not a flow chart here, so it's not necessarily that you start with one and then the other would follow. It's more like you'd say an iterative process. So you could start with industrial design, which basically cares about how machine looks like. So it's more like the UX, UI, for example, if you are if you can, for example, related to the software engineering or, for example, web applications and or desktop applications. And the mechanics, or let's say about first, let's talk about the component design, is related to what I just said before, which is basically how you design the physical, mainly the solid, but also actually the soft like spring and so on, but basically all the physical components of a machine. These physical components need to be analyzed and studied and need to be designed in a way it's basically let's say avoid fatigue and also be able to resist stress, and also basically it's safe, of course. And yeah, so these are basically the main targets. Now regarding the mechanics, basically is more about the joint static and dynamic analysis, which is also called kinematics and also kinetics. And this is basically where you can consider, so the mechanical component design is micro scale, where you take each component alone and you try to see how you can design it, what is the appropriate dimension of it. And the mechanics is more, let's say now we put these components together and we do the full analysis on it. As I said, the industrial design is more about shape, presentation, and the cost of a machine. So let's start with the mechanics terminology. So here we are not looking at the industrial design in this course, and we are not looking at component designs. These are component designs are pure mechanical, I would say. And if you look at this book, which is the third one, which is Mechanical Component Design, yeah, it's basically a great book that gives you a great overview of mechanical component design. Now, regarding mechanics component design, there are many tools that, of course, help in doing simulations as well, because traditionally, like what is in this book, traditionally you have like some, I would say, methods to analyze mechanical components, and these methods are always attached with some lookup tables, for example, where you have, let's say, a force or load, and you have some dimensions, and you would basically calculate the fatigue or other targets. Now, thanks to the advance in basically in computer science and in simulation and in 3D modelings, you can now use some simulation tools like SolidWorks, for example, which is 3D design and simulation, or Autodesk Inventor. And basically you can do test, or basically you can subject, for example, certain component on different type of loads and see if it can handle this load or not, and if not, what is the upper dimension that can handle such a load. As I said, this is out of scope of this course. Our scope is more on the mechanics part, which is, of course, itself is a big field of study. Industrial design, of course, is also not focused here, because for us, shape presentation now is not what is important. Now, regarding the mechanics, it has some terminologies. And the general definition is basically that it deals with motion, time, and forces. So we have the three physical, you can see, components. It's made up of two parts. So we have statics bodies and we have dynamics bodies, or static physical components and dynamic physical components. And yeah, so static, basically it's clear, so that's basically objects that they don't move. And dynamics, yeah, that they actually move and they change their, let's say, position if they are subjected to external forces or internal forces. Now, under dynamics, we have what is called kinematics and kinetics. Now, we'll see in the next slide the definition of both, but just remember from now, our focus is more on dynamics and kinematics, so in this course. So what is kinematics? Is a study of motion quite apart from the forces that produce the motion. So first of all, what is the meaning of study of motion? Is basically position, velocity, acceleration, rotation, and so on. This is basically motion. And the kinetics basically is a study of motion under the action of external forces. Now, kinetics is where you start to analyze dynamic stress, where you start to analyze the balance of robots, if it is subjected, I don't know, to wind power or wind force, or basically the dynamical stress or the vibration analysis. Yeah, so it's more like I have this machine, or basically the question is what would be the influence or effect of applying external forces on this machine, like I said, wind, for example. Now, kinematics is study of motion quite apart from external forces. Okay, so the main idea, if we have different objects or different links, as we'll see later, that are connected together using either static or dynamic basically joints, then the kinematics is about how motion, how position, or how velocity and acceleration would transfer from one link or one object to another object. Okay, so we don't care about external forces. And one important thing is that both kinematics and kinetics, they study rigid bodies. So what is rigid or soft bodies? Is basically non-deformable bodies. And when you apply external forces, the distance between 2 points in this body remains the same, which is basically not as soft body, which is like liquids, fluids, and where it is deformable body, because if you apply forces lead to change in shape, form of the body, which is also in the case of spring, for example. Okay. So another terminology is the difference between structure versus mechanism. Structure is a combination of resistant rigid bodies connected by static joints. So we have, as I said, different components, different solid components or rigid components or rigid bodies. And these rigid bodies are connected together by static joints. So like wheeled, for example, joints, which means it has no internal mobility that we'll talk about later, which means it doesn't have any degrees of freedom, has no relative motion between its various members. So basically they don't transfer motion between each other. And yeah, so it's basically what it's called structure or static mechanics. An example of it, I don't know, table, basically, yeah, table, chair, or as we see here, a structure that doesn't move basically, or doesn't, or actually it might move, of course, if apply external force, but doesn't have internal mobility. So there is no exchange in mobility internally in this basically machine. Now regarding mechanism, which is more about the kinematics, as I said, there is different also rigid bodies. They are called links, as we'll see later. They are connected with joints, but with movable joints. And the purpose of mechanics is to transfer motion from one basically link to another link. It has internal mobility, of course, and has relative motions between its various members, as we will see later. So now this is the mechanism. Okay, the question is, what is machine in general? Machine is just a system of different mechanisms. Like here we have a robot arm, which has basically different mechanisms. For example, it has the mechanism of the joint itself that is connecting two links of this robot arm, but also you have the mechanism of the gripper that basically used to grip stuff or objects, and you have the basically other possible mechanisms. So mechanisms is, you have mechanism as I said is where we have first of all different links connected together with a joint or movable joints, and you have different types of mechanisms. For example, mechanism A has a certain motion like a joint in a robot arm. Mechanism type B is different motion like the gripper, for example. So yeah, depending on the motion type or how the mobility or how the motion is transferred between its various members. So another terminologies, I was talking about them actually, but now it comes to their definition. We have what is called links, driver, follower, and pairs. So link is the rigid body that I was just talking about, which is a part of mechanism or structure. So also could be a part of solid bodies, but the difference is that in solid bodies the connection between two links is static. Now here links, for example, on the mechanism on the right side, we see links are numbered by 1, 2, 3, 4, and basically these are our links. So one is called frame because we'll see these mechanisms later, but basically one is frame because it is a static link. You can consider it as the base always. And whenever you're in mechanism, you see kind of hash under this mechanism. That means it is, it is basically static. Now everything in blue is movable links, and basically they are numbered as you see. They are connected with movable joint like ABC. Now links bridge connection between two or more joints element. So now joints, they connect links, and links also they connect joints, right? And basically links, they could connect two or more joints together. And for example, they must be rigid, so they must be solid. So springs are not considered the links. And the links connect two pairs, or basically the links that they connect two joints, or they have two ends basically, are connected to two joints. They are called binary links. The links that are connected to three joints or three pairs are ternary links. Now links could have basically names, or also basically functions, so different functions. So links are we have what is called the driver link, and the driver link is what is connected to the first source of the movement, or the first mover, or basically the link that if I move, it will move other links are to move the whole machine. For example, in the mechanism on the right side, link 2 is the driver, because if I rotate link 2 left or right, it will transfer the motion to link 3 and 3 to 4, and basically both would be moving corresponding, or relatively, sorry. And the follower is after what comes, that's for example 3 would follow 2, 4 would follow 3. Now the connection between the links is called pairs or joints, so basically both are correct. Now mentioning pairs and joints, we have what is called higher and lower pairs. Now it basically depends on the complexity. If we look at the right bottom side, we have table that is showing different type of joints or pairs, and this basically different type of pair, which is in the first column, their name. They have different symbols, and what is important actually is the variables that are used, which means actually the degree of freedom of that joint. Because for example, if we look at the what is called the revolute, which is the standard rotational pair or joint, which is used in robot arm, this has 1 degree of freedom only, because I can rotate it only using one angle or one variable, and it's only rotating in around one axis mainly. Okay, and the motion is circular. Now we have prism, or basically, yeah, it is also one variable, and here we have more like sliding movement. Okay, and if we look at the pictures basically, or the figures, here we have A, B, C, D. So basically A is the revolute, it has one variable rotational, and B is the prism, which is here slider, you can consider, because here we have joint sliding inside another joint, and there is 1 degree of freedom, so this joint cannot rotate or move in any other direction. It can move only in one direction, or actually along one axis only, and the changes in one axis, which is delta S here, is the 1 degree of freedom we have, which is the one variable as well. Now we have the helical basically, which is as 2, as we see, because it can rotate and slide at the same time. You can just look at figure C. Figure basically, oh sorry, helical could be this or this, so it could be slide or, so it's basically, it's like a general, it's a joint that could be converted to prism or revolute only. But if you look at the cylinder, actually this is the cylinder that can rotate and translate at the same time. So you can consider like we have a link inside the cylinder, and then of course this link, if it has no constraints, it can actually slide in or out, and also can rotate inside the cylinder, which means it has 2 degrees of freedom. And we have sphere or spherical joint there. This is basically has, we'll see an example later, has 3 rotational variables, so it can rotate along x, y, and z. Flat is same as sphere, but not 3 rotations, but rather than that is actually 3 slides, or actually, so sorry, 2 slides and 1 rotation. So it can slide along x, y, and can rotate around z. So what is lower pairs? Lower pairs is when the 2 elements of a pair have a surface contact when relative motions takes place. So basically, what is important to know about this definition is that there is a surface contact between 2 links, and this basically, the surface contact is the joint itself. Now all the mechanisms that we see on the right side, they are considered, or the joint on the right side, they are under lower pairs because they all have surface contact. Okay, so there is no point or line contact. Point or line contact, they're called higher pairs. An example of that is cams. I will show you later one example of cams. And basically there is really either line contact or point contact between 2 objects. If there's more than line or point contact, then it is lower pair, and is basically the most common joints are lower pairs. Now in robotics, as we will see later when it comes to kinematics and inverse kinematics, the higher degree of freedom in general for robot, the harder it is to model it, or to model the kinematics. That's why you would, and also for joints, also same for joints that basically are a part of these robots. The lower degree of freedom, the better. And this is why the standard joint that are used for robot arms mainly and robotics in general are the revolute and the prism. So either this or this. This, first of all, because we have 2 types of actuators or motors. These actuators could either rotate or slide, which is basically called linear actuators. And we don't have one motor or actuator that can do rotation and slide at the same time. And our goal of inverse kinematics or kinematics in general is to control these motors, of course. This is why this kind of basically we need to rely on these standard joints or standard pairs. Okay, this is one main reason. Of course, as I said, the higher the degree of freedom, also the more complicated it is. This is why also it's better to reduce the degree of freedom to be able to model a robot arm. Now, of course, the science is advancing, and we are now able to really model complex robots in general, like for example that they move like snakes, for example, which they have really high degree of freedom, but at the end they consist of small parts that they actually use simple joints like A or B. So now regarding the mechanisms, we have three types of mechanisms. We have planar, spherical, and spatial. The difference is, as stated here, planar mechanisms, basically they move in one or along one parallel, or basically they lie in so let's, if we look at this one, so this is basically the first mechanism. All motion is happening in one plane. Okay, what the meaning of that? So we have this joint, and we have this is a simple now case of planar. We have this link, this link, and this link. They are all basically on one plane, plane, or basically more parallel planes. Okay, and for example, this is one plane, this is a second, and this is a third and fourth. They are, you can consider like one plane, or basically multiple parallel planes, and this is why it's called planar. And the second type is called the spherical. Now it's a bit more complicated because all particles, or actually objects or links, they move in a spherical curves like we see here. So we have, let's look at first these three source or main joints. We have this one, this second one, and this third one. So if you look at it, it's basically it's like they are not parallel, first of all, planes, and they are for example spherical in a way, because if I have here 1, 2, 3, I could have, for example, one here, which is goes also under spherical mechanisms, and another one could be down there, and this basically creates kind of sphere of links. Now there is spatial, which is really the extreme case basically, and not the extreme but the hardest type of mechanism, because here we don't have parallel or spherical basically planes, but we have, could be they could be any directions or orientation. This is an example of spatial mechanism. Now as you will see later, actually robot arms, they are complicated, of course, they are not planar. They could be spherical, but the most common robot arms, or the manipulators are called, they are spatial mechanisms. And they are what is called open loop spatial mechanisms, because the three mechanisms that we see here, they are closed. What the meaning of that? There is no free link. Robot arm has a free link. It has actually the end effector or the creeper, which is not connected back to the frame. What the meaning here? So this is basically, again, a frame. A frame is a static object or static link. As I said, it could be the base of the mechanism, and actually you can see all the movement is not actually escaping out of the frame, so there's no free links. Same here, just to give you, maybe it's simpler to understand. If I apply a motion there, then this motion would basically move through this link, which is actually the source link, then it will move to this link, then this link, then it will come back to the frame. So it's basically why it's closed loop. So it starts here, then the frame, then and so on, and the frame. So basically there's no free link at the end. And what we see here, by the way, is a spherical joint, because this is a spherical joint, and if you remember, we said spherical joint 3 degrees of freedom first of all, and can rotate around x, y, and z. This is basically the spherical joint. Okay, so now we come to a very simple but very important actually terminology, but also topic in robotics. We're talking now about mobility or degree of freedom. Now It's basically one of the things that you would hear a lot about when you discuss robots, or when, for example, you want to buy a robot, or want to or you are, let's say, watching a lecture or presentation about robots. Basically, you would hear a lot about mobility or degree of freedom. Now, from its name, degree of freedom, and from what we have seen when we looked at the joint, it's more about variables. It's more about in how many dimensions this mechanism can move, or if not mechanism, a joint, starting from a joint, it can move. Now, mobility has two categories, I would say: mobility in planar mechanisms and mobility in spatial or spherical mechanisms. Now, what is the difference? In planar mechanisms, as I said, they move in or along one or multiple parallel plans, okay? And this is basically how we can, or basically where we use the planar mechanism, or where we use, degree of freedom for planar mechanisms. Now, if we basically, there's a very important thing here to understand. If I have, let's say, as I look here, there is one plan, right? So basically this is one plan. It's two-dimensional plan or surface. Now, if I ask a question, let's say I have here a link, which is an object that lie on this surface. So it's not flying in the earth, basically it's on this surface. If this link now is free, which is also not connected to any frame or to any other link, how many degrees of freedom does it have? So if I look at this link now on my keynote here, which is basically now we can draw or using these links, and of course this link I can do different motions on it. First, I can translate it in this way, which is basically, let's say, translating along the y-axis. I can translate it along the x-axis. I cannot translate it here along the z-axis, right? Because it is 2D. So it is a planar mechanism. I can, of course, rotate it along the x or around the z axis. So it can move, or it can be translated along x or y, or also it can be rotated around z axis. That means the link if that is not connected to anything, so if we have free link in 2D mechanism, then this link in the beginning has 3 degrees of freedom. And this is why we have here a formula, and this formula actually is used to calculate or to estimate the degree of freedom or degrees of freedom of a mechanism. And the first thing you see here basically is 3. So the idea is that, let's see, now we have different links in this mechanism. Let's see how we can reduce the mobility of this link by connecting them, and by connecting them, let's see what would be the final mobility. Now this 3 multiplied by n minus 1. So you can see, first of all, we have 3, then we are just here multiplying it with something, and then we are reducing the degree of freedom. So at the beginning we have the total degrees of freedom of the mechanism, and then we are reducing it. So if I have now let's say another link in this mechanism, so now I have 2, and now basically let's say I also have a third link here. So at the beginning I have 3 free links, and I have 1 extra special link, which is this one, and this one extra special link that I will just now give it a different color. This is what I just basically mentioned, which is called the frame or base. Now this link has 0 degree of freedom because it is the base of our mechanism, so it's basically static. So if I look now, these 4 links I have there will be always, of course, base, and I have other links, movable links. So here in total we have 4 links, and what we see here is basically how many degrees of freedoms we have initially before doing any connection between these links. Now we have 3 multiplied by n minus 1. This minus 1 represents the frame because it's always static, so it has no degrees of freedom. So in this case, we have at the beginning, we have 3 multiplied by 3, so which means we have 9 degrees of freedom at the beginning, which represent actually the 2 translation and rotation for the first link, the two translations and rotation for the second one, and 2 translations and rotation for the third one. Now this is not a free links, only this is a mechanism, and here comes the second and third part of the formula, where we start now reduce the mobility. Because if I now say let's connect this link here, let's say, so we have here first joint. Now by just doing this, I have here revolute joint. So what you need to do here is just go back and let's say I've connected bar revolute joint. What is the degrees of freedom for this revolute joint is 1. Okay, so if I go back here, this is basically I have now constrained the movement of this link, and now it can move only with 1 degree of freedom. And basically this 1 degree is only the rotation that's basically like this. Now if I do another connection between these 2 links, now I constrain the second link, and it has now only 1 degree of freedom left. And now if I connect third link, then this also has 1 degree of freedom only. And in total here basically we have now 3 degrees of freedom, right? Because we have 1 for this, 1 for this, 1 for this. So what is this formula is telling me? First we multiply 3 because free link has 3 basically freedoms in 2D plane, and minus 1 for static. So we multiply by 3 multiplied by number of links minus 1, which is the base. And in this case basically, as I said, it's called 9 at the beginning. Minus 2 multiplied by the first basically index there, which is the number. So basically if we look at IP there, it is all the joints in this mechanism, or the number of joints in this mechanism that have 1 degree of freedom, like the revolute case. Now here the H basically is it's basically the joints that they have 2 degrees of freedom, like as I said, cylinder that could have 2 degrees of freedom, or cam or gear pair. So it's basically they have 2 degrees of freedom. And if we apply this formula now, and if I look at this mechanism, I have 1, 2, 3, 4, 5 links. 3 of them are movable, 1 is static. So we start with 9 minus 2 multiplied by the number of joints that they have 1 degree of freedom. Why 2? Because these joints, each of them has only 1 degree of freedom. That means 2 would go away. So this is why we see basically minus 2 multiplied by the number of joint. And regarding this third, or basically regarding the H here, which is the 2 degrees of freedom, it is multiplied by 1 because we constrain only 1, right? And we keep 2 because it has 2 degrees of freedom. And this basically the formula. So it's, in this case it will be 9 minus 2 multiplied by 3, right? We have 3 1 degrees of freedom joint, or 1 degree of freedom joint. So 1, 2, 3. In this case basically would be then 9 minus 6, and we will have 3. And we don't have joints that they actually have 2 degrees of freedom, so it would be 0, and that means we have for this mechanism 3 degrees of freedom. Now just before going to examples, one way to directly figure out the degrees of freedom or mobility of a robot arm is actually by looking at the number of movable joints. Why? Because, as I said, for robots in general, only joints with 1 degree of freedom are considered. So that means if I have, let's say in this robot arm, we have 1, 2, 3, as I said, joints. This represents that I have 3 degrees of freedom. And if I have more, let's say I have 4, and 1 plus 1 maybe, which is number 5, could be cylinder. Not cylinder, sorry, slider, because it has 1 degree of freedom, remember. Cylinder has 2. Then it will be, for example, 6 degrees of freedom. So it's basically the number of joints in a robot arm. Of course, if there is a joint that has 2 degrees of freedom, something else, but it's not common to be used in robot arms or manipulators. So the first thing you do is to count the number of joints, or basically count the number of motors, because of course each motor is connected to a joint. And this is, of course, again, if I tell you I have robot arm that has 5 degrees of freedom, how many actuators or motors I need to use to actually move this robot arm, then you would say, since you have 5 degrees of freedom, then that means you need 5 motors. And also, if I tell you mobility is the same, so mobility and degree of freedom or degrees of freedom is the same. Okay, so here we have 3 examples. So the first one on the left is, so 3 of them are mechanisms, 3 of them are connected mechanisms or closed loop mechanisms. And basically the first one has a single degree of freedom. Why? So just here for information, as I said, this always frame. So if it is at least 2, that doesn't mean we have 2 links. Here we have 1 link, because we have 1 base always. Okay, so base is base. So wherever is located in the mechanism, it is represented by 1 frame. Now we have here 1 frame. We have 2, 3, 4 links in general. So let's say it is the same case as the example that I gave here. So we have 4 links in general, like this one. And we have actually only 1. So we have basically here different joints. That basically 1, 2, 3, 4 joints, which is different from an open loop mechanism, because in this case what we have done actually, as I said, we have connected back. So this is not a free link, which just comes to open mechanisms or open loop. Here's closed loop. And by just doing this connection, of course, I went from 3 degrees of freedom to 1, because I constrained 2 and by doing this connection. And this is why we have 1 here, and also you can apply the formula and also we'll get to 1. Now this mechanism, if you calculate it or if you estimate the mobility using our formula, then you will end up with 0, which actually makes sense, because I cannot move this mechanism at all. If I move this one, it will not move, or if I move this one, it cannot move. Now the third case is, which has multi degree of freedom, which is here m equal 2. Now if I look at this mechanism in the beginning, and if I look how many joints I have here 1, right, 2, 3, 4. 4 is basically, we will see now if this rotates or not. There's a question about mobility, but let's assume there is a rotation here. 4. 5 is a slide. So that means this actually can slide along this surface. Now if we consider, as I said, that we have 1, 2, 3, 4, 5 joints with 1 degree of freedom each. Then if I apply my formula, which will be basically 3, so 1 2 because I was counting the joints. Basically let's count now the lengths, which would be more. 1 2 3 2 3 4 5 5. So basically because 6 is the same, again 1 2 3 4 5, so we have 5 lengths. Minus 1 is 4, multiplied by 3 is 12. That means 10 degrees freedom, they are cancelled out. How? Let's see. This is the first, basically 2 are cancelled here. Okay, the second 2 are cancelled here, so now we have 4. The third 2 are cancelled here, which means we have now 6. And let's say here, so 6 basically, we still have 4 to cancel out. That means actually we have here joints, because here I'm cancelling 2 and here on the slide I'm cancelling 2. That means this actually can do kind of rotation here and can also slide. Okay, so it's basically how we come up to 2 degrees of freedom. Okay, there is we can consider another actually mechanism. Let's say actually that this cannot rotate, but it can probably, so it can actually slide along this surface, but also can be, let's say, lifted up. Okay, so it's a planar mechanism, remember, so it cannot go along the other plane, so it basically can only be either along this and or going up like a lift up or lifted down. So basically this has, so what I mean here, that this third or this joint actually doesn't rotate, so it has 0 degree of freedom, but this joint that is connecting these two surfaces has 2 degrees of freedom, which is basically sliding here or sliding up down. Now if we consider this would be also end with 2 degrees of freedom, as I said, we ended up here at 6 and we need to cancel out 4 more. This one, if it is static, is cancelling 3. Okay, now we have 1 more to cancel, and this is basically is, so this has 2, which means it's cancelling out 1, and also we ended up with 2 degrees of freedom. So we have 2 options for this mechanism. Okay, now let's take some examples, more examples. This is a mechanism, a very simple mechanism. It's called the toggle clamp here, and we have basically an arm that I can move, and while I'm moving it, I'm driving this mechanism. So we have driver, follower. This is frame, this is frame, everything static is frame. We have 1 link. This is complex link, it's called, because it has different connection, but it's actually 1 link, right? And this also 1 link, 2, and then we have 3 links plus the frame, which is 4 links. Now if I look at this mechanism, how many degrees of freedom it has, just one thing, do you consider this also as an open loop or closed loop? So the question is, the answer is actually it's a closed loop. First of all, why? Yes, here or this end is free, but actually this is a 1 link as a whole. It's called complex link, and this 1 link as a whole actually is connected back to the frame, so it's not free out of the frame. Okay, so every link that is connected to frame, that means it's not free, or actually it's not the one that's considered the open part of the open loop. So if we look at this mechanism, we first need to identify a number of links. As I said, we have frame, we have 2, and we have arm, and this is basically, so we have 4 in total. Now how many joints we have here? So this is just what is called the kinematic diagram. It is just basically to go from a mechanism to a 2D diagram. That's simpler to analyze. And this kinematic diagram is either the links are either denoted or drawn as lines or as a complex shape like triangles here. If the link is a complex itself, like as I said here, what is a complex link? As I said, complex is, first of all, as a complex shape and is connected by multiple, let's say, part of its body. Because it's a simple link, if it's represented by a line, it would have two ends, and these two ends only, they are the connected one. Now the triangle, it has different ends, so 1, 2, 3, and 2 of them are connected, and the third is not connected. This is a complex link. Okay, so this will basically the kinematic diagram of this mechanism, and we have here 1, 2, 3 link plus 4, which is the frame or base. And if we estimate the mechanism, basically it would, let's say we have 4 in total. We have 4 rotational or 1 degrees of freedom joints, and we have basically no 2 degrees of freedom joints. So yeah, so basically it's 12 again at the beginning, minus 8, and here, so we have, it will end up, oh sorry, yeah, so basically we have here at the beginning we have 4, so 4 multiplied by, so 4 minus 3 multiplied by 3 would be 9, minus 8 would be 1. So I directly basically found that I was wrong because I say 12, because whenever you look at 1 degrees or actually connected mechanisms, if a mechanism is connected, that means by definition it has 1 degrees of freedom or less. So like here, so this is basically either 0 or 1. This is, we have found it's not connected, right? Because it can actually slide, go up or down. And this is basically why I paused when I said 12, because 12, that means we have more degrees of freedom, but no, we don't. So this is basically why it's also good to not only consider formulas, but also like consider other things to estimate the mobility, like as I said, the number of motors or joints, but also whether it's closed planar mechanism or not. This is another closed mechanism, so, and we assume it's closed if this actually only sliding there. Okay, so if we look at the kinematic diagram, you can see that we have complex link first of all, which is this one, and the rest are just lines. And this can only slide here actually, which would result in 1 degree of freedom at the end. So regarding these formulas, or is that they are there's pixeling basically a bit, but I will upload the slides as a PDFs and they will be much better quality there. Okay, so this is the first part of actually our course. Now in the next, I will pause here, so as a first video, and then in the next I will talk about position analysis, which is because it's another topic that is important for the rest. So this basically was until now, which is mobility, terminologies and definition of mechanics and mechanisms and kinematics. And next we'll talk about position analysis. Thank you.